Hi, I'm Michael McLoughlin. Let's jump right in. Donald Knuth once said that premature optimization is the root of all evil, but he didn't say it wasn't fun. So I'm going to talk to you about an optimization project that started as a conversation over lunch and probably went a bit too far. And it's on the Geo Hash algorithm. So what is Geohash? It's a method of encoding geopoint data. It maps a latitude-longitude pair to a 64-bit integer or an equivalent string. It's good for indexing geodata. It has a prefix property that makes it good for proximity queries. It's very widely used. It's used in Redis internally, for example. So where we are at GopherCon right now, the coordinates are on the slide, and you can see the integer hash and the string hash. It can be taken at various precisions, and you can think of it as dividing the Earth into grid cells of various sizes. This is roughly where we are. The boxes are the geohashes of different precisions. As you zoom out, you can see you get this nesting property. So forget about string hashes for the rest of this talk. For internal use cases, the integer form is usually enough. How does it actually work? It's a two-stage process. The first step is to quantize the latitude and longitude to 32-bit values. I'll talk a bit more about exactly how that's done in a couple of slides. And then the second crucial step is to bit interleave the 32-bit values that you get. So we're going to take these two 32-bit values, consider them as like arrays of bits, and then interleave them or like zip them together into this 64-bit value. And this is actually where the prefix property of Geohash comes from, because taking a geohash at different precisions corresponds to taking variable numbers of the high bits of this 64-bit value. And as you take more and more bits, you get some bits of latitude and some bits of longitude as you go. So this is the integer geohash. How do you do it in pure Go? So at a high level, it's a two-step process. Our encode int function is going to take a latitude and longitude, and it's going to first pass it to a quantize function, and then pass it to an interleave function. So quantize is just a two-line Go function. Let's focus on what we're doing on latitude. Latitude is in the range -90 to +90. So we add 90 to get it positive, divide by 180 to get it in the range 0, 1, multiply by 2 to the 32 and convert it to an integer. And then it's pretty much the same for longitude, it's just we're adding 180 and dividing by 360. Now, bit interleaving is quite a bit more nasty, and I prefer to think of it with an intermediate step called spread, which is going to take our 32-bit values, and it's going to like spread out or explode those 32 bits into a 64-bit value, so that the original bits occupy the even bit positions. So you can see that in this diagram, and then there's some nasty bit manipulation code in Go to make it happen. And then once you've done the spread operation on both halves, the interleave is quite easy, because you just shift one of them left by one, all them together, and you've got this integer geohash. So how are we doing on performance at this point? I haven't specifically optimized that Go code, but it comes in around 27 nanoseconds per geohash, 36.5 million per second. So because this is just for fun, let's jump all the way into assembly. So the assembly to do all of that fits on one slide, 17 instructions. And yeah, this is a lightning talk. So I've skipped quite a few steps, but I'm going to try and give you a flavor of what those instructions are doing. So there are kind of three main blocks in this kernel. The first two are actually performing the quantization of latitude and longitude. And the instructions in bold here are multiplying by weird constants. Actually, these instructions are equivalent to dividing by 180 and 360. But in assembly, multiplication is faster than division instructions, so they're preferred. Now, these I really have no hope of explaining in this talk. If you've been paying close attention, you might wonder, why am I adding 1.5 rather than 0.5? This actually is exploiting the representation of floating point values as bits in registers. And there's an obscure trick where if you have a value in the unit interval, 0 to 1, if you actually add 1 to it, you can effectively read off the quantized value out of the floating point representation in bits. So that's what this is doing. We're adding an extra 1 to exploit this trick. We're moving it so that we can actually interpret the floating point value just as raw bits. And then the shift operation is actually just going to extract out the quantized value we want. All the details are on my blog post. So the remaining thing is another beautiful trick, I think. Remember that spread operation, which takes 32 bits and spreads them out into the even positions of a 64-bit word? Turns out, on AMD and Intel processors, there's an instruction that will do that in just one instruction. It's called parallel bit deposit, and it will pick up some of your low bits, and you give it a mask, and the mask tells it where to drop those bits. So actually, these 3 instructions here are going to do the spread operation for both the latitude and the longitude. And then these remaining 2 instructions, shift left by 1 and XOR to combine, and that completes the interleave. So this kernel here gets us this like massive speed up, 2.3 nanoseconds per geohash, 431 million per second. And we're actually getting close to the cost of calling a function. Now, I really don't have time to explain this, but I just want to give a tease that you can go even further down into this rabbit hole. If you use SIMD vector instructions, you can do 4 geohashes at once, and that's just the beginning of it. That gets us to 1.13 nanoseconds per geohash, 880 million per second. So assembly in Go can be really fun. If you're using special processor instructions, you can get like massive speedups, and the full details are on my blog.